Hey everyone, and welcome. Today we're going to tackle one of the absolute biggest questions you can possibly ask. Are the fundamental rules that run our entire reality, the laws of physics, are they actually set in stone? Or could they be changing over the vast expanse of cosmic time?
All right, let's dive right in. I mean, we all kind of take it for granted that the laws of physics are the same today as they were billions of years ago. But what if that's just not true? What if the source code of our universe has been getting quiet edits over the eons?
So, this is the question at the very heart of our investigation today. It really challenges one of the most basic assumptions in all of science, this idea that the rules are the same everywhere and for all time. If we found out they weren't, it would completely upend our understanding of, well, everything. So, to get our heads around this massive question, we first need to understand what these rules actually are. In physics, they're not really rules so much as they are numbers, what we call fundamental constants. Okay, let's break this definition down because it tells us something really profound. These aren't just numbers we can cook up with our theories. No, they are numbers we have to actually go out and measure in the real world. They are, in a very real sense, the universe's factory settings, the fundamental numbers that make everything work the way it does.
And this is the perfect way to think about it. It's like a recipe. If you tweak the amount of gravity or the strength of an electron's charge, even by a tiny, tiny bit, you could get a universe where stars can't even ignite, or where atoms can't form stable bonds. The recipe for our universe, the one we live in, seems to be incredibly fine-tuned. And, this whole idea that these values might not be fixed, it's not some crazy new theory. Way back in 1937, the legendary physicist Paul Dirac thought it was a bit weird that these numbers should just be what they are for no apparent reason. He argued it was actually more likely that they've evolved over time to get to where they are today. So for our story, let's zoom in on one of the most important characters, the fine structure constant. We call it alpha. To put it simply, this number dictates how strongly charged particles, like electrons, react to light. Basically, it's the master volume knob for all of chemistry and electricity. And here it is. This is its value. It's about 1 over 137. It's just a pure number, no units, which to physicists makes it extra special, extra fundamental. But why this number? Why 137? Honestly, nobody has a clue. It's one of the deepest mysteries in all of science, and it's the constant we're going to go hunting for. So how on earth can we check if alpha was different billions of years ago? I mean, we can't build a time machine, right? Well, it turns out astronomers have something even better. The secret is the universe itself. Because light takes time to travel, when we look at a galaxy that's a billion light years away, we're not seeing it as it is today. We're seeing it as it was a billion years ago. The farther we look out into space, the farther back in time we see. The universe is our time machine. And here's the brilliant method scientists use. We find these things called quasars. They're the incredibly bright centers of faraway galaxies, and they act like giant cosmic backlights. As that light travels for billions of years to get to our telescopes on Earth, it passes through ancient clouds of gas. And the atoms in those clouds leave a very distinct fingerprint on that light. Now, this fingerprint is the absolute key. When we take that quasar's light and split it into a rainbow, a spectrum, we see these little dark lines. Think of it like a barcode. And here's the magic. The exact spacing between those lines for any given atom depends directly on the value of the fine structure constant alpha at that place and at that time. So, by measuring the spacing in that ancient light, we can actually measure what alpha was billions of years ago. How cool is that? Now, this wasn't just some one-off measurement. A massive study took this idea and applied it on an absolutely industrial scale, using data from the Sloan Digital Sky Survey. Yeah, they didn't just look at a handful of quasars. The final tally was an incredible 13,175 of them. Using a data set this huge lets you get an incredibly precise measurement and helps smooth out any random noise in the data. So what did all this data actually show? Well, the researchers grouped the quasars by how far back in time they were looking. Now, pay attention to that last column. That shows the measured change in alpha. But look closely at the numbers. In every single time period, the little bit of change they might have measured is way smaller than the margin of error, the plus or minus number. And that's the key takeaway. Any tiny flicker they saw is statistically the same as seeing no change at all.
So, after sifting through light from the ancient universe, light that's older than our own planet, what's the final verdict from this absolutely heroic effort?
And here it is. This is the grand finale, the combined measurement for how much alpha has changed over nearly 8 billion years. Now, that first number is the tiny change they measured, but the second number, the one after the plus minus sign, that's the uncertainty, the margin of error. And notice something really important. The error is twice as big as the measurement itself. In science, that means your result is statistically indistinguishable from zero.
Let's put that crazy number into perspective. It means that the fundamental strength of electromagnetism has stayed the same to within a few thousandths of a percent for more than half the entire age of the universe. That is an absolutely astonishing, almost unbelievable level of stability. So, the crucial bottom line is this. Based on the very best evidence we have, the fine structure constant just doesn't seem to be changing. At least for the last 8 billion years, this fundamental rule of our universe has been, well, exactly what we call it, a constant. But this incredibly precise result isn't just an answer to a question. It's a really vital clue in the much bigger puzzle of reality itself. So, why does this stability matter so much? Well, this result has huge implications. First, it confirms a core pillar of science, the idea that the laws of nature are consistent through time and space. Second, it's a major reality check for some of our most advanced and exotic theories, like string theory. A lot of those theories actually predict that these constants should change. This result tells those theorists to go back to the drawing board. And finally, on a much grander scale, it tells us that the universe's basic recipe, the one that allows for stars, planets, and us, is remarkably stable. The cosmic ground beneath our feet is firm. And this result leaves us with a really tantalizing thought. Because the search isn't over. Physicists are looking for tiny changes in all the other constants, with even more powerful tools. Alpha, the fine structure constant, seems to be rock solid, but it makes you wonder, what happens if, one day, we find a rule of the universe that actually is changing? That discovery wouldn't just be big news. It would rewrite physics as we know it.